In this video, we're going to continue our discussion from part one of this three-part series to discuss the concept of expected value. And an expected value of a distribution or a random variable is just the mean. In fact, that's another name, the mean of the distribution. The key difference between a mean here and the sample mean we calculate from data is that the expected value is a probability-weighted average of the possible outcomes. And this is we should think of this as the mean of a population or a probability distribution as opposed to the mean of data. So our first example, if x is the roll of a die, then its distribution is described by this picture, 6 equally likely outcomes. The expected value, which we indicate with this notation, e of x, or the mean of x, which we indicate with the Greek letter mu, is the probability-weighted average of the possible outcomes. Possible outcomes are 1, 2, 3, 4, 5, 6, and they get equal weight 1/6 each. So when we work that out, we get an expected value of 3.5. Now, what does it mean that the expected value is 3.5 if we can't roll a 3.5? Well, the best way to think about it is that if we rolled many times and we averaged the rolls that we got across many repeated tries, the average of those many rolls would come close to 3.5 as we rolled more and more times. So that's what we mean by the expected value of this distribution. Let's look at another example. In the I-origins experiment, the relevant random variable here is the number of questions answered correctly, or number of correct responses out of 25 tries, when you have a 1/3 chance of getting each one right. And the probability weighted average of those is going to be 25 times 1/3, right? So intuitively, you can think of that as, well, I've got 25 tries, and each time I've got a 1/3 chance of getting it right. So on average, I would expect to get 8.33 correct. Okay, but the way we said that we calculate an expected value is we take the probability-weighted average of the possible outcomes. The possible outcomes are you could get 0 correct, 1 correct, 2 correct, up to 25. So that's the possible outcomes. We need to weight each one by the probability of that outcome. So this says the probability that we score 0 correct, probability we score 1 correct, probability we score 25 correct, and so on. Those are just the heights of the bars. Okay, and we've got those probabilities in a spreadsheet. So here's the same distribution. These are the numerical values of those probabilities. And we use those probabilities to take the weighted average. And if we work through that arithmetic, that gives us the answer of 8.33. And you can see that explicitly on the other tab of the spreadsheet. Here I've got the possible outcomes. Here are the probabilities. And if I use the function sum product, I'm doing this times this plus this times this plus this times this, that calculation, and that works out to be 8.33. So that confirms that this indeed gives us 8.33. Now, this might seem like a long way to get the answer that we could have gotten more directly just by going 25 times 1/3. So let's try to understand what the relationship is between these two ways of getting the same answer. The key is to understand that the total score across 25 tries is the sum of the scores on the individual cards, the individual 25 cards. On each card, you have a 1/3 chance of getting it correct if you're a random guesser. Right? A random guesser has a 1/3 chance of getting it correct, 2/3 chance of getting it incorrect. So each of these is either a 0 or a 1. You get a 1 if you got it correct, and a 0 otherwise. And when we add those up, that's the total score across the 25 tries. The expected value of this random variable, which is just the score on each try, the expected value is the probability weighted average of the possible outcomes, which are 1 and 0. So when we weight those by the probabilities, we get an expected value of 1/3. And now here we need to use a key property, which is that the expected value of the total score is just the sum of the individual expected values. So that gives us 25 times the expected value of any one of these. Right? So we're adding the same number 25 times, and each one of these is equal to 1/3. 25 times 1/3 gives us 8.33. In the next part of this video, we will see how to use this way of thinking to get the standard deviation of the distribution.